Hey everybody, Mr. Bells again. This video is a Geometry A video. It's coming for you for section 5-3. It's where we're starting to get some shortcuts that prove why triangles are congruent without having to show all 6 parts. Okay, so we're going to start here in the student journal. If you have a student journal, that'd be awesome. Again, the student journal note-taking. First off, congruent figures. We know congruent figures are figures whose all their parts match up from one figure to another figure. Rigid motion, like reflections, rotations, translations, and glide reflections, all get us from one figure to another figure. But we're going to start with our first one right now. Are these two triangles congruent? Well, there's a theorem that basically says this. It's got something called SAS, which means that there are two sides and an angle that happens to be between those two sides. So it's not any two sides in an angle, but it's the angle that's between the two sides. So you can see on a triangle here and a triangle here, I've got two sides and the included angle marked congruent, and then two sides, single dash, double dash, single dash, double dash, like that, and the included angle in between it. And if we have those things, if we have a side angle side for one triangle that matches up perfectly with the side angle side for another triangle, then those two triangles must be congruent. Okay, so again, side and a side, side and a side. So just to be clear though, watch this. If I draw these two pictures, and I've got this, this, and this, and I've got this, this, and this, these are not the same things. So these two triangles would not be considered congruent, because this is a side, an angle, and a side, and this is a side. See how it skips this angle and then a side. So this single mark would have to actually be over here in order for these to work. This one would be called, in terms of markings, would be called an SSA situation. And we haven't talked anything about that specific situation yet, but this would be an SAS. But since they're not the same, then we can't say that they're congruent. So this would be a no. Okay? So that would be one example of the shortcuts for it. And you'll see that on some of the other ones we'll have it. So let's do one of these formal proofs and see if you guys follow through on some of this stuff. It says given BD is perpendicular to AC. So BD is perpendicular to AC. So I'm not going to go through all the statements and reasons, but I'm going to kind of give you some gists of some things. Well, if that's true, then this is, since they're perpendicular, then this is a right angle. And if that's a right angle, then that's a right angle. And if those are both right angles, then those angles are congruent to each other. Okay? And then you can also see that BD is congruent to itself. That's the reflexive property. So now you can see on triangle ADB that you've got a single mark, an angle, and a double mark, or an SAS situation. And then over here on triangle CDB, and remember I've got to put them in the order in which they are. I still have that same single mark, double mark, and that angle. Therefore, these two things have to be congruent. Okay? So again, I'm not giving you all the formal things. I want you to try those on your own. But that's kind of the basic idea, because they are perpendicular. Then that's a right angle. If that's a right angle, then that's a right angle, and all right angles are congruent. You could also go perpendicular, it's right angle, it's 90 degrees. If that's 90 degrees, and that's 90 degrees, and so on down the thing, and then two 90-degree angles are congruent. A couple different ways you can state that all out. Those gives you those angles congruent, and then reflexive property gives you that side. So if we came down here, this would be a different one. It says prove JNK, that's this triangle right here, is congruent to triangle MNL. That's this triangle right here. And I think this is hopefully pretty obvious. You've already got a side and a side and a side and a side on those two triangles. All I'd have to be able to show is that those two angles in the middle are congruent, and you're like, hey, isn't that the blank theorem? And I would say yes, if in your head you just said vertical angles theorem. So if I was to do a formal thing on this one, I would say this, that Jn is congruent to Mn, and Nk is congruent to Nl. That was given. You can see it's up there. Then I could say that angle JNK is congruent to angle JNK and MNL, and that's the vertical angles theorem says that. That's from a couple of units ago. Then in terms of markings, you can see that this one gives me an S, this one gives me an S, and this one gives me an A. And it just so happens to be that those triangles, S's and A's, are in the order that we need them to be, SAS. So then I can say triangle JNK is congruent to triangle MNL, and that's by the SAS Triangle Congruence theorem. And it's okay if you just put SAS for that now. Okay, so I'm going to kind of skip through a couple other things for you here. This one would be using a circle, and it shows that those two things are congruent. These sides are equal. These sides are equal. They're all equal to each other because of the definition of a radius of a circle, that they have to be, because a circle is defined to be the set of all points equidistant from a certain point P on the circle. Therefore, all the radiuses have to be congruent. Now you can see you have a side angle side and a side angle side on both of those, and that's kind of where we're at on those things. Okay, so 5-4 is a separation of it. It kind of deals with a couple more things. So we might have talked about this before. I'm going to kind of throw it through there to you. You know what? I think I'm just going to do this as a separate video. So we're going to call 5-3 good. 5-3. It's using SAS in the shortcut SAS. Yeah. We'll talk to you later. That's 5-3.